Hello everyone, welcome to the MUDE week of machine learning. In this lecture we are going to learn about a classic method of unsupervised learning, the principal component analysis. What is principal component analysis and how do we implement it? We will find out the answers together in this lecture. As learning objectives, by the end of this lecture you will be able to explain the maximum variance formulation of principal component analysis and implement principal components analysis. There are the two topics in this lecture. The first one is continuous latent variables models in unsupervised learning that I use for dimensionality reduction. The second topic is principal component analysis, or in short PCA. First, let's briefly recall continuous latent variables models in unsupervised learning and continue with the use of the models for dimensionality reduction. In unsupervised learning, we introduce this latent variables set that can influence how we observe the input data X. Discrete latent variables models represent the problem of clustering. Continuous latent variable models represent the problem of dimensionality reduction. Principal component analysis is a classic method for dimensionality reduction. But before we get into PCA, let's first understand what is dimensionality reduction. Dimensionality reduction transforms data into a lower dimensional latent space while retaining some properties of the data. These concepts can be too abstract yet to understand. So let's see an example. Here we have some images of the handwritten digit number 3. These images are synthetically generated by one handwritten digit 3 by moving the digit in the horizontal and vertical directions, and also rotating the digit 3 by different angles. In the pixel space, these images have 100 multiplied by 100 pixels. So they are essentially data having 100 multiplied by 100. That is 10,000 dimensions. That is a large dimension number. However, across this data set of images, there are only 3 degrees of freedom of variability corresponding to horizontal translation, vertical translation, and rotation. This means the data samples can be simply projected into a lower dimensional space, and we will call it this the latent space. In this space, only 3 variables are needed to describe the original image data. In other words, we can reconstruct all 10,000 pixels images from only 3 latent variables. This is an example of dimensionality reduction from 10,000 to 3 variables. In reality, handwritten digits images data will have more degrees of freedom that entail more latent variables representing variations in digit size, digits from 0 to 9, different colors, individual writing styles, and so on. But even considering these variabilities, we still need much fewer variables than the 10,000 pixels. From what we understand so far, some main purposes for dimensionality reduction of data include reducing the computational cost when handling big data. Also for better understanding and visualization of high-dimensional data, particularly for feature extraction, because high-dimensional data are normally difficult to analyze and visualize. It is also for improving data compression and transmission by reducing the data volume. There are also some other purposes depending on the field of application. Note that in the example of handwritten digits, the latent space is a nonlinear transformation of the image data. So we reduce the dimension number from 10,000 to 3 by nonlinear transformations. Here we consider linear transformations with principal component analysis. Now let's find out what is PCA and how to implement it. Principal component analysis finds a linear projection of the input data samples such that the variance of the projected data is maximal. In other words, PCA captures the direction of axis of maximal variation in the data, called the principal components. Let's visualize this definition by using a 2-dimensional data set as an example. Here we have a 2D data set with samples denoted by red dots. These data samples are projected onto the new direction denoted by the magenta line, also called the first principal component U1. The projected data are denoted by green dots, and they should have maximal variations between each other. Here we can visualize the variations of the projected data. You can try to project the data onto a direction different than U1, and you will find that the variations of the projected data is smaller than those from the principal component U1. So far, we have been learning the maximum variance formulation of PCA. In this formulation, we aim to find the direction of maximal variations in the protected data, as shown in the right figure. There is also another widely used formulation of PCA called the minimum error formulation. The minimum error formulation finds a data projection that minimizes the projection error J, which is defined as the average square error between the original data and the projected data. This error between xn and x tilde n is shown in the right figures as blue lines. Note that these two formulations of PCA are mathematically equivalent. In the rest of this lecture, we will focus on the maximum variance formulation. In PCA, we are given a set of observations of xn, where n is the number that goes from n to capital N, and xn belongs to d-dimensional real numbers. The goal of PCA is to project the data xn into an m-dimensional space that maximizes the variance of the projected data x tilde. In this dimension, number m should be smaller than d, the original data dimension. Now let's look at PCA from a simple perspective by assuming that m equals to 1. So we want to project the data onto a one-dimensional space, and the direction of this space is the vector u1, also known as the first principal component. To proceed, we should define the mean of the data xn as x bar, and the data covariance matrix S using xn and x bar. The covariance matrix is introduced in linear algebra and probability theory in case that you need a recap. With the data mean and the data covariance, we can define the goal of PCA as maximizing the variance of the projected data given by this formula, where we have to transpose the u1 multiplied by u1 equals to 1, so that the u1 is a unit vector. Now let's work together to find a solution to this maximization problem. We want to project data xn to a one-dimensional space in the direction u1 that maximizes the variance of the projected data x tilde n. Here are the steps we follow to solve this problem. On the right, we have a visualization of how the direction u1 can be found by trying different directions. In the steps, we will see how we can solve this problem mathematically. In step 1, we project data samples to u1, so we have a scalar value, the transpose of u1 multiplied by xn. In step 2, we can compute the mean of the projection, the transpose of u1 multiplied by x bar n, and then in step 3, we can compute the variance of the projection, the transpose of u1 multiplied by the covariance matrix X multiplied by u1. PCA aims to maximize the variance of projection by finding the argument of the maximum variance. To solve this problem, we need to introduce a Lagrange multiplier lambda 1 in the step 5 to enforce the constraint that u1 is a unit vector. Now we want to maximize the projection variance plus lambda 1 multiplied by 1 minus the transpose of u1 multiplied by u1. In step C6, by settling the derivative with respect to u1 equals to 0, this quantity in step 5 has a stationary point when the equation holds. In linear algebra, when this equation holds, it means that the u1 is an eigenvector of S. And finally, in step 3, we multiply the size of the equation by the transpose of u1, and we have the variance equal to lambda 1. Remember, PCA wants to maximize the variance, and the variance now equals lambda 1. This means the variance is maximized when we set u1 equal to the eigenvector of S with the largest eigenvalue lambda 1. Now we have a solution to the maximization problem the variance of the projected data is maximized when U1 is the eigenvector having the largest eigenvalue lambda 1 of the covariance matrix S. So we don't need to search for the direction U1 anymore by trying all possible directions. We can directly have this eigenvector directly from the covariance matrix S. This eigenvector is also known as the first principal component. In fact, for a general case of projection onto m-dimensional space, when m is larger than 1, the variance, the projected data is maximized when u from 1 to m is equal to the m eigenvectors of the covariance matrix S corresponding to the m largest eigenvalues. In this way, we can have the first m principal components by finding the m eigenvectors of the covariance matrix S. Here we see an example of the first principal components and the second principal component from PCA. We can observe how the first principal component captures the largest variations in the data, while the second principal component captures the second largest variation of the data, and in a direction that is orthogonal to the first principal component. Be aware that when implementing PCA, to have the eigenvectors, the computational cost of the full eigenvector decomposition for a matrix of size D multiplied by D is a function O of D cubed. This can be computationally expensive when we are dealing with data dimension D that is super large. However, if we are projecting the data on the first m principal component, it means we only need the first m eigenvectors. The computational cost can be largely reduced to a function O of m multiplied by d squared. This technique is widely used in the program function of PCA that you will use in Python and in other languages. Now we know the solution of PCA. So how do we decide the dimension number m we need for our data? Because we actually measure the discarded or explained variance with respect to the dimension m, we can choose m such that the large percentage of variance is preserved from the input data. By doing so, we can preserve most of the variation of the data at a lower dimension. So let's see an example of a specific data set. Here we plot the proportion of explained variance with respect to the dimension m. The proportion of explained variance is computed using the equation over here, where TR of S denotes the trace of matrix S. In this example, say we want to choose an m so that the proportion of explained variance is larger than 90%. By looking at the dashed line representing 90% in the figure, we know we can choose m equal to 2 as the corresponding proportion of larger than 90%. Now let's see some applications of PCA. The first example is PCA applied to feature extraction. In a complex structure, we can install many sensors at different locations to monitor potential damages of the structure. By using PCA, we can reduce the dimension of measured data to a much smaller number of latent variables, while retaining most of the variations in the original data of a structure. In this way, we can use a small number of variables as features to help identify damages of the structure. Another example is PCA for data compression. This is a similar example of handwritten digits we saw at the beginning of this lecture. The original image of the left has 789 pixels, so 789 dimensions. By applying PCA, we can have a compressed image with only 184 dimensions on the right. Here PCA reduces 600 dimensions from the original image, while preserving the data variability with an explained variance of about 96%. You can still tell it is a 0 from the compressed image. Note that the dimension can be even further compressed by introducing probability or some nonlinear PCA, for instance, probabilistic PCA or kernel-based PCA. In this lecture, we learned that dimensionality reduction transforms data into a lower dimension latent space while retaining some properties of the data. As a representative method of dimensionality reduction, the PCA finds an optimal linear projection of data onto a lower dimension space while preserving most of the variability of the data. In PCA, the eigenvectors of the data covariance matrix correspond to the largest eigenvalues and are the principal components. The lower dimension number for PCA can be selected by measuring the discarded or explained variance with respect to the dimension number. Now we are at the end of this lecture, and hopefully you can now explain the maximum variance formulation of PCA and implement the PCA. Here are some reading materials that can help you to understand the content of this lecture, and now it's time to implement the PCA. Thank you for your attention.